Okay, we're going to look at some differentiation rules. The first one is the constant rule. So if we have a function that's a constant, then the derivative of that function is 0. And alternatively, we may express this rule as d dx of c equals 0. So we're taking the derivative with respect to x is what we're looking at. And here's just a little proof of that rule, and you'll see that in several of these examples. You're not responsible for the proofs, but I think it's good to see where these came from. And an example, as you can see, find the derivative of f of x equals 9, and we know that is 0. And that's going to be true if you look at the proof up here using the limit of the difference quotient, that whenever you're taking the limit of a constant, it's always going to be 0. And so we have this nice rule now that we can follow when we're doing derivatives. And that's the same with many of the rules. So we have the power rule, where we have n is a positive integer, and if f of x equals x to the n power, then the derivative of that would be you bring that n down and take 1 away from it, and that gives us our derivative. And again, it can be represented as d dx of x sub n, the derivative of x to the n power with respect to x. So we develop formulas for derivatives of this type of function in stages, beginning with positive integer powers. Now note, this rule doesn't apply to functions where the exponent is a variable. So for example, 2 to the x power or x to the x power. Remember, n is a positive integer. So let's look at an example here. So what if I have f of x equals x to the 7th power? Well, we bring that 7 down front and we take 1 away from it. So we have 7x to the 6th power for our derivative. And for example, what if f of x is just x? Well, think of that as x to the 1st power. So we'll bring the 1 down and take 1 away. 1 minus 1 is 0, and anything to the 0 power is 1. And so my answer would be 1. And I'm going to show you, we're going to look at the proof. I'm not going to spend a lot of time on it, but I do want you to see that this was derived from the limit of the difference quotient. So if you want, you can pause here and look at this proof and see if you can follow along with it. What about the sum, difference, and constant multiple rules? Let f of x and g of x be differentiable functions and k be a constant. Then each of the following equations hold. So we have the sum rule. The derivative of the sum of a function and a function g, a function f and a function g, is the same as the sum of the derivative of f and the derivative of g. So basically, if we're going to take a derivative of a sum of two different functions, then we can take the derivative of the first function and add it to the derivative of the second function. Okay, and the same thing when we look at the difference rule. Let f of x and g of x be differentiable. Now you notice these things have to be true in order to be able to use these rules. K is a constant. And then we have the difference rule, which is basically very similar to the sum rule, except we're taking a difference. We can take the difference. We can take the derivative of f of x minus the derivative of g of x, and we come up with our new function, and that's really what this is showing us here. We have j of x equals f of x minus g of x, so j prime of x would equal f prime of x minus g prime of x. And here we're going to look at the constant multiple rule. So what if we have a constant in front of or multiplied by our functions? So if we want to take the derivative of a constant times a function, then we would have that constant times the derivative of the function. And again, for j of x equals k of f of x, then the derivative of j prime of x would be k, the constant, times the derivative of f of x. And again, here is the proof of the sum functions. What is the derivative of the sum of differentiable functions? And so you can kind of see here where this has run through shows you how to use the limit of the difference quotient here. So again, I'm not going to spend a lot of time on the proofs. This isn't a proof course. Okay, so let's look at an example here. Find f prime of x for f of x equals x to the 7th plus 10. So we take, if you go back and look at our rules, we take the derivative of the one function, which is x to the 7th power, which becomes 7x to the 6th. And then here's that constant plus the derivative of the constant, which is 0. So we're left with 7x to the 6th power. All right, what if I have f of x equals 8x to the 4th plus 9x squared minus 1? Again, because of the sum rule and difference rule, we're going to use both of them here, and the constant rule. So as you can see, we're using all three rules. We would take the derivative of 8x to the 4th, which is 32x cubed, plus the derivative of 9x squared, which is 18x, minus the derivative of 1, which is 0. And so we would be left with 32x cubed plus 18x. All right, let's look at another example. So here, this one's, we're looking at a quotient. But I can, since that's a 3, we can pull that out front, and that becomes 1/3. And then take the derivative of x cubed, which is 3x squared, of 2x squared, a constant rule there in our power rule, 2 times 2x. And then, of course, the derivative of any constants, 0. And if we simplify this, we end up with x squared plus 4/3 x. All right, the product rule is the derivative of a product, the product of derivatives. And here we're going to say no. The derivative of a product is not the product of derivatives. And here's what, looking at an example, f of x and the derivative of f of x, g of x and its derivative. And so if I multiply the two derivatives, what do we get when we multiply these two? Okay. F prime of x times g of x is 1. G prime of x, 1 times 1. But f of x times g of x equals, and if we multiply these, I get x squared minus 1. And then if I find the derivative of this, it ends up being 2x, which is not the same as the product of the two derivatives. So we have a product rule here. F of x and g of x must be differentiable functions. Then we take the derivative of their product. We take the derivative of f of x times g of x plus the derivative of g of x times f of x. And so j of x equals f of x times g of x, which this would look like j prime of x equals f prime of x times g of x plus g prime of x times f of x. So here's our product rule. And using the definitions, we can prove that. So again, we can look at the proof. If you want to spend a little more time, pause here and look over the proof and see how it comes out with our product rule. Okay, so let's look at an example of using the product rule. So here we have a function h of x, which is made up of two functions, x plus 2 and 2x squared minus 3. So we'll label each one of those one f and one g function. And I usually like to work to the side and find the derivative of f of x, which looks like it's 1. Find the derivative of the g function, which would be 4x, and then plug them in. And so the next step here, you can see what is f prime of x? It's 1. And then g of x is 2x squared minus 3 plus x plus 2, my f of x function, and then times the derivative of of g of x, which is 4x. Okay, and then we can simplify this into 6x squared plus 8x minus 3. And here's another example. What if it wants you to actually find h prime of 2 for h of x equals f of x times g of x, and then f of 2 equals 3. So f prime of 2 equals negative 4, g of 2 equals 1, and g prime of 2 equals 6. So h prime of 2 is f prime of 2 times g of 2 plus f of 2 times g prime of 2. And then we can fill in, we were given all of these, so we can fill these in. And we find that h prime of 2 equals 14. So we still follow the product rule here. Of course, we have a quotient rule, and let f of x and g of x, again, be differentiable. And then you can see, and I'm going to drop down here because this one sometimes is a little easier to understand. If we're taking the derivative of two functions in a quotient, then we have f prime of x times g of x minus g prime of x times f of x. And they're both divided by g of x squared. And again, this rule or this proof is very similar to the product rule, but I'm not going to show you that slide. Again, you're not responsible for the proofs that you see here, but we do want to know how to use the quotient rule. So here we have a function, and we can let the numerator be f of x, denominator be g of x. Find the derivative of each one, and then plug it into our rule. All right, so what's the derivative of f of x? It's 1. G of x function minus f of x times the derivative of g of x. And then all is divided by g of x squared. And then we can just simplify our numerator. And sometimes they simplify quite a bit, and sometimes they're not. There's not much more we can do with that particular function. We do have what's called an extended power rule. If f of x equals x to the negative n, what would f prime of x equal? Well, let f of x equal 1 over x to the n and use the quotient rule. So again, now here, this u and v, it would be f. You could call it f over g. They're just using the variables u and v to represent our functions. Let u equal 1, right? And v is going to be the denominator, just like the regular quotient rule. And then we plug it into our rule. And so we end up with negative n x n minus 1 over x to the 2n power, which ends up with negative n x minus n minus 1. So we kind of use this, show how we can extend the power rule to negative integers. Just remember, when n equals 0, we use the constant function rule, x to the 0 power prime. If it's a constant, it equals 0. So we've shown that we can use the power rule for all integers, and then later on we'll show that it can be used when n is a fraction and when n is a real number. So that was kind of a neat way of deriving that rule. So let's look at what we have here. So you can see we have x to the fourth plus 2 over x. So the derivative, we can use the sum rule here, and we'll also use that extended power rule that we were looking at. We'll move that x to the numerator, which becomes x to the negative 1. Pull down the negative 1, subtract 1, and you can see we end up with 4x cubed minus 2x to the negative 2. And then we can drop that back down by using our exponent rules that we learned way back in college algebra. And again, here's another example. We have x squared times 2 over x squared plus 5 over x cubed. And you can see we distributed our x squared and simplified our function. And now we'll use our power rule and end up with negative 5 over x squared. And of course, as we've been talking, you can combine several different rules. As you can see here, we have k prime of x, and we're looking at our constant rule, product rule. We have several rules here together. So you can use several different rules. And again, we can extend the product rule, where what if we're multiplying more than just 2 functions? It could be extended to 3 functions or even more than that. Okay, so let's look at this combination here. And so it looks pretty ugly. We've got 2x cubed and then this k of x function. And we still follow the quotient rule and the product rule, because up here we're multiplying as well as using the quotient rule, which can be pretty tedious, as you can see as you work through this function. So we can look at here, we used the quotient rule. And then down here, we added the product rule, where we have the addition. And like I said, it can get pretty tedious when you're looking at something this long. But I think it's good to see that how you can use several different rules at one time. Okay, let's shift gears just a little bit before we end here. Determine the values of x for which f of x equals x cubed minus 7x squared plus 8x plus 1 has a horizontal tangent. So f prime of x, so once we find our derivative, we set that equal to 0 and see what values give us 0, because remember, that's our slope. If we set it equal to 0, we're saying we have a slope of 0, which is a horizontal line. And so when we do that, we factored and we find out where x equals 2/3 and x equals 4. That's where we have horizontal tangents for this particular function. So we'd have one here at 2/3 and one here at 4. And one more example. Use the following figure to find the indicated derivative if it exists. Find h prime of 4. So we have f of x plus g of x, so we find those derivatives. F prime of 4 plus g prime of 4 equals 2 over 2. And then you can look at what we're looking at here. Here's f of x and g of x function. And we see at 4, what do we have? Okay. And then g of 4, again, is horizontal. This one is 2 over 2, because we're looking for the tangent line here, or the slope of this line, and the slope of this line, so we end up with 1. And this kind of shows you that rise over run, how we come up with 2 over 2, and how we come up with 0.